Um, at this point, I would like to present to you another method that is used for the evaluation of the energy band structure of the electrons. Up to now, we have seen the free electron case, case plus perturbation, the tight binding model, and in the first case, the electrons that were considered were electrons free or nearly free, so electrons that may be described by plane waves or nearly plane waves for what concerns their wave functions. Then in the tight binding case, we had electrons that could be described by core wave functions or atomic orbitals, so electrons that are strongly bound to the ion. In this case, in this new picture, what is done is to try to find the general expression for the electronic wave function that may combine both the, let's say, plane wave behavior that the electron has when the electron doesn't feel a strong effect of the ionic potential with a, let's say, oscillating behavior that you have, similar to the one that you have for core wave functions when the electron feels the strong ionic potential. So the idea is to find a combination of the two approaches. And this method is, the acronym of this method is OPW, where OPW stands for orthogonalized plane wave method. In a while, we will see why orthogonalized. So the idea is to start with the initial point. With this, the starting wave function in this case is not as in the time binding case the atomic orbital, but is a combination of a plane wave that recalls the free electron picture, plus a combination of core levels. And those core levels may be, for instance, the solution of the tight binding model. So you may perform a first calculation to find what are the actual expression for the core electronic levels. So you have psi of k that comes from the time binding approach, and then you use that wave function in this orthogonal plane wave method to build up the starting wave function for the calculation. So the idea is to make this kind of combination to have both kind of behaviors for the electron. One question at this point could be, why should I use core wave functions instead of using many plane waves? Because with the plane waves, let's say, with the plane waves, you may approximate any possible wave function. So in principle, you may just do the Fourier transform of something, and then you have a number of plane waves for instance, the trial wave function. But the point is that the larger is the number of functions that you use for the calculation, the larger is the computational power you need to solve the calculation. So one tries to use as a number of functions in the problem that is the lowest possible. So in this case, instead of saying, okay, I just use many plane waves to approximate all the behavior of the electron in any possible condition, you combine the plane wave that represents the behavior when the effect of the potential is small, and core wave functions that represent the situation where, on the other side, the effect of the ionic potential is quite strong. The coefficient BC for the moment is arbitrary, but is generally fixed applying an additional condition. And the additional condition is that this phi of k, so the the prototype for the wave function has to be orthogonal to the core levels for any arbitrary C prime index. So the orthogonalize stems from this condition. So if you apply this condition, you have that an arbitrary core level So at this point, you may split the integral into two integrals. One has just the phase. Then the second is the cross product of one core wave function and a combination of core wave functions. If you have chosen the set of core wave functions so that they are orthogonal with each other, then just one of those survives in this cross product. So you have just the BC coefficient that corresponds to the index C prime of the core level that you have used for the scalar product. So here we have just BC prime because and that is fine if you have chosen the proper normalization for the core levels. So the solution is that BC prime is minus the integral of a core level times the phase. And this will be quite useful later for the calculation. And what I would like to do now is not to, let's say, go through all the details of the application of the orthogonalized plane wave method, but just to see what are the consequences of this kind of approach. Because when you, let's say, when you try to build up the wave function useful for the solution of the Schrödinger problem, you may not directly use this trial wave function here because this does not satisfy the block requirement. Because psi of k are core levels, so those core levels are actually block wave functions, so those are fine. But for what concerns the plane wave, if you make a translation in the direct space, then a phase appears, and that is fine. But if you make a translation in the reciprocal space, you have not exactly the initial phase. So we have to make some modification to the structure of the initial wave function so that also the combination of the phase plus the core wave functions is actually a block wave function. So what is generally done is to define a new phi of k that is a combination using as a coefficient of this, as an index of this summation, the vectors belonging to the reciprocal lattice. And this, the coefficients are C of G and the terms of the summation are the trial wave function we saw before, but with an index that now changes as k plus g. And what is the effect of this change? Concerning the core wave function, let's say it was a block wave function before, it's actually a block wave function now. So nothing changes from the point of view of being or not being, not from fulfilling or not fulfilling the block condition. But if you consider the plane wave, now in place of k at the yeah, I just write that. Now, when you consider just the phase, in the summation you have k plus g within the phase, not just k. So if you make translation of an arbitrary G, then you may just redefine the index of summation and you have exactly the initial wave function. So the fact to make this combination where the wave vector of the combination includes vectors belonging to the reciprocal lattice transform this phase or a combination of many different phases into a block wave function. So using this kind of combination now, both parts of the trial wave function, that is the plane wave plus the core part, both build up a new wave function that is actually a block wave function. So with this modification, we have on one side the possibility to make a combination of different trial wave functions, and we also fulfill the condition that is required by the block theorem for the use of this wave function for a problem where we have a periodical potential. So at this point, what is generally done is to use this wave function for the Schrödinger problem. And I just say this quite fast. The point is, instead of solving the Schrödinger equation, one defines a functional, so something that depends on the wave function that you decide to use. This functional is defined in this way. So I don't want to give you a full justification of the use of this functional, but what can be demonstrated is that if one wave function is a solution of the Schrödinger equation, then the same wave function is such that that functional has a minimum value for that wave function. So the equivalent, instead of solving the Schrödinger equation, what you require is what is the set of wave functions such that this functional has its minimum value. So the question now is, so what are the phi k's such that E of phi k is minimum? And to switch from the approach that goes through the solution of the Schrödinger equation, so to switch from that approach to this approach is useful due to the fact that if you in general, when you find the minimum, when you look for a minimum, what you do, you make the derivative of that with respect to a parameter, and you ask that that derivative is equal to 0. So in this case, the problem we have is not to single out the wave function, as we already have the wave function. The problem is to find the coefficients. So the question, this question is set in a different term, that is, when the derivative of that functional with respect to C of G is equal to 0. And depending on the number of G's that you want to use for this combination, you have many different equations. So you have one equation for each parameter of the combination. So this is just one equation here, but actually, if you have, for instance, 10 coefficients, C of G, then you have 10 equations when you require that the derivative of the functional with respect to that coefficient is equal to 0. So if you solve that system of equations, then at the end you are able to find the C of G, the values of the different coefficients. So in this case, the problem is reset in terms of solving a system of equations, and each equation corresponds to the fact that you require that the derivative of that function with respect to one of those coefficients is equal to 0. So my point was not to go through this method, but to say we have the opportunity to determine the values of the CG coefficients. So what happens when we have solved all those equations, and we have found what are the CG values that fulfill the condition of making the functional stationary. So at this point, if So if we suppose that we have solved all those equations, so we have the CG values. At this point, the idea is if we have the solution, let's try to rewrite the solution. So just let's try to expand this expression so to distinguish, so to single out the contribution of the phi k of plus g wave function given by the phase, and the contribution to the phi k plus g wave function given by the core levels. So let's just rewrite the initial trial wave function. So we had a sum of g over g of coefficients and phi k plus g of r. So we have a sum over g of cg. Then we have the phase, and in this case, we have k plus g. Then a summation over the core levels of bc, and psi, in place of k, we have k plus g of r. Now, we may split the summation into two parts. One part is sum over g cg e to the I k plus g times r. The second part is sum over g sum over the core values of cg bc psi k plus g core of r. In this case, we may label this first part of the wave function as phi of k of r, and just to use the same terms that are used by the textbook, this wave function is called valence part of the its index is labeled by the letter V that stands for valence. I ask your attention just in one point. In general, when you discuss about semiconductors, you discuss about valence band and conduction band. So valence is opposite of conduction. In this case, we are discussing electrons that are supposed to be conduction electrons that are supposed to move within the solid. So in this case, valence is used in a sense that in the semiconductor physics is used with another meaning. So please now consider that V for valence is a synonym of conduction electrons. So electron that is able to propagate through the solid. And then, so we have this first part that is just made just by plane waves, and this second part where we have core levels. We may now split this part considering the fact that BC is known. So BC is related to the core levels and to the phase. So if we just consider this part here, this part is a sum over G, sum over the core levels, C of G, then BC, we may replace this expression for BC, the one we found before. There is a minus sign, then the integral of psi of k core level conjugated. I use r prime to distinguish that from the r that is the variable of all the other wave functions. Then we have the phase. In this case, we have to use k plus g because we are considering the core wave function corresponding to k plus g, r prime, d3 r prime, and then we have the core level corresponding to k plus g as a function of r. At this point, we may recall the fact that the core wave functions are actually block functions. So for block function, k plus g is equal to k. So any arbitrary translation in the reciprocal space does not affect the expression of the wave function. So we may remove all the g's from the index of the core wave function. So in doing that, the summation over G affects just the phase because the G is left only in the within the phase. Due to that, I take the summation within the integral and I place the summation just in front of the phase. So yeah, I have minus sum over the core wave functions. Then I have the integral of psi of k core conjugated r prime. Then I have the sum over g of c of g e to the I k plus g r prime d3 r prime. And then I have the core level of k as a function of r. And if you notice this part here, the sum over g of cg e to the I k plus g r prime, that is actually the definition of phi of k, because that is the combination where we have just the phases. So I replace that expression within this integral. May I switch to another sheet? Yeah, please. Yeah, so the final step is that the phi k of r that was the initial choice is equal to the phi k valence of r, that was the initial definition that we set, minus the summation over core levels of psi of k core conjugated of r prime times valence function of r prime d3 r prime times the core level as a function of r. So in this way, we have just written in a different way the starting wave function. So what happens if we introduce this wave function into the Hamiltonian? So the Hamiltonian in this case, we know that this Hamiltonian has a solution because we have already solved the problem. So we know that E of k has, let's say, E of k has a value, is known. So it's a number that we know because we already have solved the problem. Let's just try to replace phi of k with this new expression that we have just found for phi of k. So in this situation, we have that H, the Hamiltonian of the system, applied to the valence part of the wave function minus the summation over C of psi core conjugated R prime phi valence R prime D3 R prime is equal to EK phi k valence of R minus the summation over C of the core level phi k valence R prime D3 R prime times the core wave function. Yeah. At this point, we may leave the valence wave function to the left, to the right, and take the summation over the core levels to the left. So we have the Hamiltonian applied to the valence function. Then, when you apply the Hamiltonian to the summation over C, you have that what you have within the sorry, I missed the core level at the end of the summation. What you have within the integral is just a number. So you actually apply the Hamiltonian to psi of k. Psi of k is a solution of the problem concerning core levels. So you know what is the energy corresponding to the core level psi of k. So when you apply the Hamiltonian, you are left with minus the energy of that core level. Sorry, I have to take that within the integral. So I have summation over C of so each wave function is multiplied by the energy that corresponds to that wave function, and that is a core level, a core energy value. Then I have plus the same summation over C that comes from the other side and is multiplied by the energy of the valence function. This is the summation over C of psi of k C conjugated R prime phi k of V R prime V3 R prime. Then I have C of k core R times the energy value that we already know corresponds to the solution of the problem when we use the full combination with plane waves and core levels. And this is equal to EK times just the plane wave part of the initial wave function. At this point, we have again Hamiltonian applied to the plane wave part. Then we may combine the two summations that we have here, since they are similar apart from one coefficient. And this is psi of k C conjugated R prime valence R prime D3 R prime. Then we have the E of k, that is the solution of the actual problem, minus EK core, that is the core value corresponding to the core wave function. And this should be equal to E of k phi k valence of R. Yeah. Now, please have a look to this term here. In the Hamiltonian, what you expected to have, what you expect to find within that Hamiltonian, you have the kinetic term plus the ionic potential U of R. So you apply those operators to the, you are just applying those operators to the plane wave part of the wave function. If you consider this term here, this is a sort of operator. If you consider as the, let's say, wave function of this problem, the plane wave part, just phi of k of v, then phi k of v is actually included in this expression because you have that phi k of v is here. But that is, in this case, you have not just a multiplication. You have that the wave function is included in an integral. So this is an integral operator applied to phi k of v. So here you have plus v, where the definition of v includes the knowledge of the wave function. So, and this is called pseudo potential. Why pseudo potential? Because if you notice this structure, you have the plane wave part of the problem that somehow interacts with the core wave function because you have a cross product between phi and psi k. So this is a sort of interaction between the plane wave part of the problem and the core levels. In addition, if you consider this pseudo potential applied to phi of k, and you want to evaluate the expectation value of that potential over the phi k of v, so just the plane wave part of the problem, you have a summation over c of, in this case, you have two integrals, one over r prime and the other over r. So you have ckc conjugated r prime phi k valence of r prime d3 r prime, and this was the initial integral. Then you have phi of k valence of r conjugated. Then you have psi of k core of r d3 of r times ek minus ek core. If you notice the two integrals, in one case you have core conjugated times phi. In the other case, you have phi conjugated times core level. So one integral is the conjugated of the other integral. So this is the square modulus of the integral. So it's positive. This difference is the difference between the solution of the Hamiltonian for this valence wave function minus the energy corresponding to a core level. A core level has for sure an energy that is lower because the core level feels the strong effect of the ionic potential. So the energy of that level is lower than the energy corresponding to the solution of the Hamiltonian we are considering now. So also this difference is positive. So the expectation value of that operator over the plane wave part of the wave function is a positive number. Differently, if you consider the expectation value over the ionic potential, that is negative because the interaction between the electron and the ion has a negative sign in front. So what is the final conclusion? This final conclusion is, in principle, you should have U of R in the problem where U of R may be strong, in particular close to the nucleus. So if you consider U of R as the ionic potential, at this point, you have a strong contribution to the Hamiltonian coming from that potential. But if you now consider this new Hamiltonian applied to the just to the plane wave part of the wave function, and you define this new Hamiltonian as the old Hamiltonian plus this pseudo potential, then the overall potential that you have in this case, that is the sum of U of R plus the pseudo potential, then in this case, U of R is negative, pseudo potential is positive, and the pseudo potential, sorry, U of R is negative in particular at the ion position. The pseudo potential is positive, and where is particularly positive? In that integral, you have core wave functions. So that integral is different from zero, in particular when you are close to the nucleus, because you have the core functions there. So where the U of R is strong and negative, the pseudo potential is positive. So you have a balance between the negative contribution coming from the ion and the positive contribution coming from the interaction with the core levels. Because in this case, you may consider that to be a sort of Coulombian repulsion between the plane wave part of the wave function and the core wave functions. So in this case, you may expect that the sum of U of R and of the pseudo potential is still negative, but not as strong as U of R. And the conclusion is why I wanted to reach this point, because in the initial part of this discussion concerning the electronic levels, I told you that in some situations you may use an approach that is the free electron approach plus a perturbation, and that perturbation should take care of the effect of the ions. But in general, the effect of the ions may not be considered to be a perturbation because you have a strong ionic potential. But if instead of considering just the ionic potential, you also include the contribution of the core electrons that are there somehow screen the nucleus and interact with a positive interaction with the free electron, let's say, then in this case, you may expect that the actual potential that the free electron feels is not as strong as the ionic one. So thanks to the presence of this pseudo potential, the nearly free electron approximation has now a justification, because in that case, one may assume to use not the actual ionic potential, but the sum of the ionic potential and the pseudo potential. Okay, it's yeah, 11:07, so I think it's better for me to stop now because while there is the lesson of Professor Moretti and you have to reach your house. So if you do not have questions or comments, I will stop here. Okay,